Good morning. Today we are going to start the chapter Nitro Compounds. Introduction. Nitro compounds are an important class of organic compounds which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atoms by nitro group. Nitroarenes, that is, nitro compounds in which NO2 group is directly attached to benzene ring, can be prepared rather easily and have been used as synthetic reagents since long. But nowadays, even nitroalkanes are being prepared and used on a large scale. Structure of nitro group. Nitro group is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or dative bond between nitrogen and other oxygen. But actually, nitro group is stabilized by resonance and is a hybrid of two equivalent contributing structures. The resonance hybrid structure is confirmed by the fact that the bond length of each nitrogen oxygen bond is 121 picometers or 121 angstroms, which is intermediate between NO single bond length, that is 136 picometer or 1.36 angstroms, and N double bond O double bond length 115 picometers or 1.15 angstroms. In case of nitroarenes, resonance of nitro group with the ring can also take place, giving rise to additional contributing structures for the molecule. It will be interesting to note that nitro group is isoelectronic with carboxylate anion. Nomenclature of nitro compound. Nitro compounds are named by writing the word nitro before the name of the parent compound. The number of nitro groups and their positions are also suitably indicated. Classifications of nitroalkenes. Nitroalkenes are termed as primary, secondary, or tertiary according as the nitro group is attached to a primary, secondary, or tertiary carbon atom. Preparation of nitro compounds. Preparation of nitroalkenes. Nitroalkanes are usually prepared by the following methods. First, vapor phase nitration of alkanes. These reactions involve the substitution of a hydrogen atom of the alkane by a nitro group. It is carried out in the vapor state by heating the alkane with nitric acid at about 700 Kelvin. Limitation of this process. During nitration of higher alkanes, all possible isomeric nitro compounds are formed. Moreover, rupture of carbon-carbon bonds also take place, leading to the formation of nitroalkanes containing lesser number of carbon atoms. For example, nitration of propane results in the formation of mixture of 4 nitro compounds. That is, when propane is heated in the presence of nitric acid, it gives rise to 1 nitropropane in 25%, 2 nitropropane 40%, nitroethane 10%, and nitromethane 25%. Due to the formation of complex mixture of products, this method is not used for the laboratory preparation of nitroalkanes. However, the method is widely used for the commercial preparation of nitroalkanes since they are used as industrial solvents only. Mechanism. The reaction is believed to involve the formation of free radicals, but the mechanism is not well established. Second, action of silver nitride on alkyl halides. This is the method generally employed for the laboratory preparation of nitroalkanes. When heated with silver nitride, alkyl halides undergo nucleophilic substitution to form nitroalkanes, along with small quantities of alkyl nitrides. This is because NO2 is an ambident nucleophile. However, the mixture of alkyl nitride and nitroalkanes can be separated by fractional distillation. Oxidation of amines. When an amine in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is obtained. Preparation of nitroarenes. Nitroarenes are almost invariably prepared by direct nitration of arenes. The nitrating agents generally used are: first, concentrated or fuming nitric acid; second, mixture of concentrated or fuming nitric acid and concentrated sulfuric acid. Sometimes fuming sulfuric acid is also used. This mixture is the most commonly used as nitrating agent. Third, mixture of concentrated nitric acid and acetic anhydride or boron trifluoride. Fourth, acetyl nitrate obtained by mixing nitrogen pentoxide and acetic anhydride. Fifth, nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent. The choice of nitrating agent to be used for nitration of a given compound depends upon the following two factors. First, nature of the compound to be nitrated, and second, number of nitro groups to be introduced. In nitration of aromatic compounds containing electron releasing or activating groups such as NH2, OH, CH3, the reaction takes place radially at the room temperature by employing concentrated HNO3. In some cases, even dilute HNO3 can be used. For nitrating compounds containing electron attracting or deactivating groups such as C double bond COOH, or when it is desired to introduce more than one nitro group, a suitably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. It may be remembered that nitro group itself is also a deactivating group. Nitrobenzene and meta-dinitrobenzene, for instance, can be obtained from benzene under the conditions. Mechanism of nitration. Nitration of aromatic compounds, like other aromatic substitution reactions, is electrophilic in nature and involves a nitronium ion, NO2 positive, as the attacking electrophile. The mechanism may be summed up as follows by considering the nitration of benzene with nitric acid sulfuric acid mixture. First, generation of electrophile. Second, formation of carbocation ion. Third, proton transfer from the carbocation to yield the final product. Evidence in favor of the above mechanism. It has been shown above that aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as an electrophile reagent, is generated in a preliminary step and brings about further reaction in two steps. The first step is a slow rate determining step involving the addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involves the elimination of a proton from the intermediate ion by the heterolytic cleavage of CH bond. This mechanism has been fully supported by isotope tracer technique as explained below. If an aromatic compound labeled with deuterium, the heavier isotope of hydrogen having a mass of 2 amu, is subjected to nitration, it is found that the rate of substitution of deuterium is the same as the of ordinary hydrogen or protium. In other words, no isotope effect is observed. Since a carbon deuterium bond is broken more slowly than a carbon protium bond, the absence of isotope effect in aromatic nitration can be justified only if the rate determining step of the reaction does not involve any cleavage of carbon hydrogen bond. This means that the final step involving the abstraction of proton through the cleavage of carbon hydrogen bond cannot be the rate determining step. Therefore, the step leading to the formation of carbocation must be the rate determining step, as it does not involve any cleavage of carbon hydrogen bond. Once formed, the carbocation loses the proton relatively fast to form the final product. The absence of isotope effect also rules out the possibility of a single step mechanism for nitration. This is because single step substitution cannot take place without the cleavage of carbon hydrogen bond. As such, it must exhibit isotope effect, but this is not so actual practice. Hence, aromatic nitration is a stepwise process in which the formation of carbocation is a rate determining step. Comparison of nitration of arenes and nitration of alkanes. It may be noted that nitration of arenes takes place at relatively low temperature, whereas nitration of alkenes require a very high temperature. This may be due to the fact that the nitration of arenes involves the initial formation of an electrophilic reagent, while the nitration of alkanes is supposed to involve the initial formation of a free radical. The formation of free radical takes place through homolysis and requires stronger conditions than the formation of electrophile, which take place through heterolysis. As such, nitration of arenes takes place more easily than nitration of alkanes. Nitroarenes cannot be prepared by the action of silver nitrate on aryl halides because of the very low reactivity of aryl halides toward nucleophilic reagents. Now, physical properties of nitro compounds. First, physical state. Nitroalkanes are colorless, oily liquids when pure. They have pleasant smells and are sparingly soluble in water, with the exception of a few compounds, including nitrobenzene, which are yellow, oily liquids. All other aromatic nitro compounds are yellow crystalline solids. Nitrobenzene has an odor of bitter almonds and is known as oil of mirabin. Solubility and density. All the nitro compounds are heavier than water. Nitroalkanes are sparingly soluble in water, while aromatic nitro compounds are insoluble in it. They are, however, readily soluble in organic solvents such as alcohol and ether. Third, stability. When heated strongly, polynitro compounds decompose with explosive violence. Fourth, boiling points. Due to the presence of highly polar nitro group in their molecule, ni- nitro compounds have strong dipole-dipole interaction. Consecutively, consecutively, consequently, they possess high boiling points, much higher than hydrocarbons of comparable molecular masses. However, most of the nitro compounds are volatile in steam. The melting and boiling points of nitro compounds gradually increases with the number of nitro groups as illustrated ahead. Nitrobenzene has a melting point 278.8 Kelvin and a boiling point is 463 Kelvin. Metadinitrobenzene has melting point 363 Kelvin and boiling point 576 Kelvin. 135 trinitrobenzene has a melting point 395 Kelvin and boiling point is not known. Chemical reaction of nitroalkanes. Important chemical reactions of nitroalkanes are as follows. First, acidic nature, tautomerism. Nitroalkanes containing alpha hydrogen atoms, that is, primary and secondary nitroalkanes only, exhibit acidic behavior and form salts in the presence of strong alkalis. The acidity can be attributed to the facts that, first, nitro group has a strong electron withdrawing inductive effect, that is, minus I effect. Second, the anion formed after the removal of the proton from nitroalkanes get resonance stabilized due to the ability of the nitro group to accommodate negative charge. It is interesting to note that if the salt formed by nitroalkane is acidified at low temperatures, the oily drops of nitroalkanes do not separate immediately, but we get another form of nitroalkane known as nitro form, which slowly changes into nitro form. This is due to the fact that primary and secondary nitroalkanes exhibit tautomerism. The tautomerism form being nitro or iso form and nitro or nitronic acid form. The tautomeric equilibrium between the two forms lies almost completely towards the nitro form because it is stabilized by resonance of nitro group. Nitro form is relatively stronger acid than nitro form. An important feature of nitro form is that it can act both as an electrophile and an nucleophile. Unlike primary and secondary nitroalkanes, tertiary nitroalkanes and nitroarenes do not have any alpha hydrogen atoms. As such, they exhibit neither acidic character nor tautomerism. Second, reduction of nitroalkanes. Reduction of nitro compounds is one of their most important reactions. The reduction of nitro group take place in stages. The product actually obtained depend upon the nature of reducing agent and pH of the reaction medium. Thus, nitroalkanes can form different product on reduction. Reduction in acidic medium. When reduced in acidic medium, nitroalkanes form primary amines. Second, catalytic reduction or reduction with LiAlH4. Reduction with lithium aluminium hydride or H2 in the presence of nickel, palladium or platinum catalyst also yields the same product. Third, reduction in neutral medium. If the reduction is carried out in a neutral solution, a hydroxyl amine derivative is obtained. The hydroxyl amines are readily oxidized to correspond nitroso compound on warming with Tollens reagent, which get reduced to metallic silver. This reaction is used as a test for nitro compounds under the name Baker-Mulliken test. Third, hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkanes undergo hydrolysis to form carboxylic acid and corresponding salts of hydroxyl amine. Secondary nitroalkanes are hydrolyzed to ketones and nitrous oxide by boiling with concentrated HCl. Tertiary nitroalkanes and nitroarenes are not hydrolyzed by acid. Fourth, Neff reaction. When sodium salts of primary and secondary nitroalkanes are hydrolyzed by boiling with dilute sulfuric acid, aldehyde and ketones respectively are obtained. The reaction proceeds through the nitro form of nitroalkanes. In this reaction, the nitro form act as an electrophile. Fifth, action with nitrous acid. Primary, secondary, tertiary nitroalkanes exhibit different behavior towards nitrous acid. First, primary nitroalkanes react with nitrous acid to form nitrolic acid, which dissolve in NaOH to produce a red solution. Second, secondary nitroalkanes react with nitrous acid to form pseudo-nitrols which have blue color. but do not dissolve in NaOH. Third, tertiary nitroalkanes and nitroarenes do not react with nitrous acid since they do not contain any alpha hydrogen. The above reaction can be used for distinguish between primary, secondary, and tertiary nitro compounds. Sixth, halogenation. When treated with halogen, that is chlorine or bromine, in slightly alkaline solution, primary and secondary nitroalkanes undergo halogenation at alpha position. Nitromethane on chlorination in alkaline medium gives trichloronitromethane, CCl3NO2, also known as chloropicrin. Tertiary nitroalkanes do not undergo halogenation because they do not have alpha hydrogens. Seventh, condensation with aldehyde. Due to the presence of active alpha hydrogen atoms in them, primary and secondary nitroalkanes undergo aldol type condensation with aldehyde in the presence of a base to form nitroalcohols. 8. Manic reaction. This is condensation reaction which involves formaldehyde, ammonia, or a primary or a secondary amine, generally taken as hydrochloride, and a compound having at least one active hydrogen, such as primary or secondary nitroalkanes. The reaction can be used for preparing nitroamines, diamines, etc. Chemical reaction of nitroarenes. Nitroarenes are chemically rather inert compounds. The nitro group is firmly attached to the nucleus and cannot be replaced by other atoms or groups under ordinary conditions. Their important reactions are as follows. First, acidic nature. Unlike primary and secondary nitroalkanes, nitrobenzenes do not have any alpha hydrogen atom. As such, they do not exhibit acidic character or tautomerism. However, nitro compounds having two or more nitro groups attached to the benzene ring are somewhat acidic in nature due to the strong electron withdrawing effect of the nitro groups on the benzene ring. Second, reduction. The most significant reaction of nitro compounds in their reduction under different conditions to give different products. As a result, as already stated, the reaction takes place in stages and the nature of the final products depend mainly on the pH of the reaction mixture. We will illustrate the reduction of nitroarenes under different conditions with the help of nitrobenzene. First, reduction in acidic medium. On reduction in acidic medium with an active metal and acid such as zinc and HCl or tin and HCl, nitrobenzene yield aniline. Mechanism. The mechanism proposed for the reaction involved a number of steps in which addition of electrons from the metal and protons from the acid takes place and nitrobenzene free radical anions and nitrosobenzene free radical anions are formed as intermediates. Second, catalytic reduction. Reduction of nitrobenzene with H2 in presence of nickel or platinum catalyst also yields to the formation of aniline. Third, reduction in neutral medium. When reduced in neutral medium, example with zinc dust and ammonium chloride solution, the reaction stops at hydroxylamine stage. Reduction in alkaline medium. On reduction in alkaline medium, nitrobenzene yields different products depending upon the nature of the reducing agent employed. These products are actually formed by further reaction between the primary reduction product, that is nitrobenzene and phenyl hydroxylamine. Azoxybenzene is formed by condensation of nitrosobenzene and phenyl hydroxylamine. There is sufficient evidence to show that azobenzene is formed through the intermediate formation of azobenzene and its further reduction. Hydrazobenzene is similarly formed by further reduction of azobenzene. Reduction with lithium aluminium hydride. Of nitrobenzene with lithium aluminium hydride also yields azobenzene. Electrolytic reduction. When reduced electrolytically in weakly acidic medium, nitrobenzene gives aniline, but on electrolytic reduction in strongly acidic solution, nitrobenzene yields para-aminophenol due to rearrangement of phenyl hydroxylamine first formed. Electrolytic reduction in alkaline medium yields azooxybenzene, azobenzene, and hydrazobenzene. Seventh, selective reduction. In case of compounds containing more than one nitro group, it is possible to carry out the selective reduction of the one of the groups by employing a mild reducing agent such as ammonium hydrosulfide or sodium polysulfide. The reduction is known as Ginin reduction. Third, electrophilic substitution. Nitro group, being an electron withdrawing group, has a strongly deactivating effect on electrophilic substitution reactions of benzene nucleus. However, under strong conditions, nitro compounds may undergo electrophilic substitution in meta position with respect to nitro group. It may be noted that nitrobenzene does not undergo Friedel-Crafts reactions. Fourth, nucleophilic substitution reactions. The nitro group has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature. But this very electron withdrawing influence of the nitro group makes the benzene nucleus liable to be attacked by nucleophilic reagents. Thus, unlike benzene, nitrobenzene on heating with sodium hydroxide gives small amount of ortho and para nitrophenols. Mechanism of the reaction may be outlined by considering formation of para nitrophenol. Replacement of nitro group. In case of polynitro compounds, one of the nitro group itself can be replaced by nucleophilic groups. Hence, here is the completion of our chapter. Thank you.